All right, in this video, we're going to work through the last two examples in your 6.2 Honors Pre-Calculus class notes. The time permit, more examples, more practice. So example 14, right, this really is just, can you read and draw a right picture and set up the problem? So you are pulling another box, this time up a ramp that makes a 20-degree incline with the floor. So right away, the first thing I would do is draw a 20-degree incline. And you're pulling a box. All right, so here's my box. And you pull with a force that has magnitude 90 pounds and acts at a 35-degree angle to the inclined ramp. Now this is interesting. Not 35 degrees to the horizontal, 35 degrees to the inclined ramp. So if I'm pulling here, then parallel to the inclined ramp, I am pulling at a 35-degree angle. And that force has a magnitude of 90 pounds. So the magnitude of F equals 90. All right? Determine the magnitude of the effective force pulling the box up the ramp. Ooh, okay, so again, interesting. The magnitude of the effective force, not in the horizontal direction, but the effective force in pulling the box up the ramp. So in that case, it's actually asking how your box is moving, right? What force is effectively being used going up the ramp? So again, that would be my vector projection of my force F, not onto the horizontal, but on the incline itself. So this right here is my effective force vector right there for pulling the box up the ramp. So in fact, do I need this 20-degree angle here at all? No, it's actually not necessary. All I need is this right triangle right here that says this force magnitude is 90. The magnitude is what I'm trying to find, so I'm going to call that X, and I know this angle right in here is 35 degrees. And so what can I say? Well, I can say cosine of 35 degrees is X over 90. So the effective force, X, is 90 times cosine of 35 degrees, which is approximately, punching that into my calculator, I'm getting 73.7. And what is it measured in? This force is being measured in pounds, lbs, of effective force. And that's it. So again, the challenge in this problem is just, can you draw the picture? Can you set up? Do you know what's not relevant data in this case? This problem would be very different if the question was, right, determine the effective force horizontal component. Like if I was asking you to actually find F's component form, that would be different, right? But we'll let that go. We'll be done with that. And example 15 is very similar to a homework problem number, I think it's 43 in the textbook. So let's work through this one and see how you would do this one. So given that u is -2, 5, and that u dot v is the scalar -11. Ooh, real fast, what does it mean if the dot product of two vectors is negative? All right, since I know that u dot v is equal to the magnitude of u times the magnitude of v, and those are both positive, times cosine of the angle between them. When will this be negative? It'll be negative when cosine of theta is negative. When is cosine negative? In quadrant 2. So this means that these two vectors have an obtuse angle between the two of them. Just fun fact, not necessary for this problem. The magnitude of v squared is 10, and I'm asked to find the components of v. So right off the bat, I see this and I see this and I think, okay, the magnitude of v I know is the square root of v1 quantity squared plus v2 quantity squared. And so if I am looking at that magnitude squared, right, all this squared just means that 10 is going to equal v1 squared plus v2 squared. So that's a quadratic equation. What else can I use? If I look at this, u dot v is -11. Well, again, u is -2, 5. Dot v is v1, comma v2. And if that equals negative 11, I can actually perform the dot product on my components here and say, well, that's going to give me a linear equation in V1 and V2. Negative 2 times V1 plus 5 times V2 is negative 11. So what I've got, that's an equation in V1 and V2. That's an equation in V1 and V2. I've got a system of equations. 2 equations with 2 unknowns. Unfortunately, this one's quadratic, so this is going to be a little bit more challenging than just when I've got 2 linear equations and 2 unknowns. But it's okay. Step 1, solve this for one of my variables. Since that's negative, I'm going to say plus 2v1 to both sides. And then I'll divide everything by 5 to give me that v2 is 2 times v1 minus 11 all over 5. And I'm going to do my best to write my subscripts ridiculously small so we don't confuse those as being numbers. They're subscripts. So if that is my v2, I'm now going to drop that in here, and I'm going to rewrite this over here and say 10 is equal to v1 squared plus quantity 2 times v1 minus 11 all over 5 quantity squared. So 10 is v1 squared plus, when I multiply this all out, 2v1 minus 11 times 2v1 minus 11 is going to give me 4 v1 squareds minus 22 v1 minus another 22 is minus 44 v1s, and then 11 squared is 121. That will all be over 5 squared, which is 25. All right, let's clear our denominators. Let's multiply absolutely everything by 25. So that's going to give me 250 is equal to 25 v1 squareds plus 4 v1 squareds minus 44 v1s plus 121. So in solving this, we're going to have, if I say subtract 250 from both sides so I can get a quadratic, right? That's quadratic. So I'm going to have 0 is equal to 29 v1 squareds minus 44 v1s. And then, all right, 250 minus 121, that difference there is going to be 129. So minus 129. It factors. It does. It might not be easy to see, but I promise I picked ones that factor. So 29, the only way to multiply 29 by 2 numbers is 29 and itself. So I've got 29 v1 times v1. All right, 129. 129, 9, 10, 11, 12. The sum of these is 12, so I know it's divisible by 3. This is 3 times 43. All right, here I need negative 44. So negative and negative, so one of these is plus, one of these is minus. So if I do 3 times 44, if I do 3 times 29, 29 times 3, that's going to give me 27, carry the 2, 6, 87. 87 and 43, if I subtract 43 from 87, that gives me 44. Ooh, so where does the minus go? Where does the plus go? I want to do 29 times 3 will give me 87. But I want that to be negative because I really want this to be negative 87. So I get a net of negative, so I want a plus 43 here, and that's how that's going to factor, which means I'm going to have 2 possible solutions. Either, we'll do the easier one first, either v1 equals 3, that's the easier one. If v1 is 3, then that means that v2, using this equation right here, that means v2 is going to be 2 times 3 minus 11 all over 5. So v2 is going to equal 6 minus 11. Well, that's negative 5 over 5 is negative 1. So that means my vector v could be either v1 is 3, v2 is 1, or that's one solution. Or the other solution is when this guy, if v1 is negative 43 over 29. All right, that's less fun. If that's my solution, then again, v2 is going to be 2 times negative 43 over 29 minus 11 all over 5. I'll save you a little bit of time. This works out to being negative 81 over 29. So my other possible solution for v is, again, v1 is negative 43 over 29 or negative 81 over 29. So those are my 2 oh, sorry, -1. Whoops, copy. -1 right there. 3, -1. 3, -1, or -43/29, -81/29. All right, that is the last two examples of our class notes. Again, this problem here is very similar to, I think, number 43. Number 41 is very similar to problem 13 up here with the line and the parallel line. And in the previous video, I actually don't think I quite finished. In the previous video where we were doing example 13, yeah, we got as far as finding the two unit vectors. So how do we find the ordered pairs P? We take the ordered pair A, which is -5, 0, and from there I would want to draw this vector. I'd want to go backwards 0.37 and up 0.93. So really it's -5, 0 plus -0.37, 0.93. And that's going to give you that ordered pair for P1. And then for P2, again, -5, 0, if you add those there, -5 and 0.37 is going to give you -4.63-ish, and this will be -0.93. So actually those are ordered pairs, not vectors. So let's write them with parentheses, the ordered pair, 0.1 and 0.2 for our example 13. And again, this example is very similar to homework number 41 in our assignment. So that's where we will stop.